I've got my own physical calculator today. It'll just save me zooming too many out and in windows. So basically, we're going to look at how do you do this particular sigma. Sigma equals n equals 1 to 100 of e to the n. Well, let's do n e to the n, right? Now, if you wanted to see what that looked like, well, when you plug in 1, the first guy is this one, the second guy is this one, and then you'd finish eventually with 100 e to the 100, and I've just decided to change the question. I'm going to make it 10. And the reason I'm going to make it 10 is that e to the power 100 is so big, I think the calculator would die on me. The calculator can only go so far and then it keels over. So we're adding up the first 10 of these. We could certainly do it by hand, right? You could do it that way, but we're going to choose a different pathway. So second list, move this over a little bit more. There we go. Choice 5. Second list in ops, choice 5. N e to the n is going to be n e to the power of n. Then comma n again, comma 1, comma 10. Are we getting a little bit more comfortable with the sigma notation calculator, right? So you hit enter and some ridiculously ugly big decimal appears, and I'm just going to pretend that the book said to the nearest whole number. Actually, I put my comma in the wrong place. It's about 328,175. Cool. And for my last one of these, hopefully that'll be plenty of practice. I'll pick 7. It's as random number as anything. Let's do n over the sine of n. Just random fraction. So I'll clear this one out of the way. List math number 5, that gets me the sum. List option 5, that gets me the sequence. I want an n, and I want to do divide, and I want to do sine of n. Should be able to then do comma n, comma 1, comma 7. And this time the answer is some ugly decimal, and let's pretend that the book says to 2 decimal places. Right, I'm going to be leaving the sigma for a little while now. Before I do so, is there any issues with that, or do you all feel comfortable about how to use the TI-84 to do sigma questions similar to these ones? You feel good? Yes.
Could you go through the button pressing one more time? It took me a while to find it on my calculator.
Ah, you got a different calculator or just a different version of mine?
No, I just haven't used a graphing calculator in forever.
Okay, not a problem. Right, so I'll just write down here, that way it'll be on the video as well. If you go to Canvas, you will find that I have a video of me pressing buttons just like this as well. And I also think, I could be proved wrong there, that I've got the written instructions on that video as well. But let's do this right now, because right now is important. So you hit the blue button, start. That gets you a thing called list. So blue button, start. And so that's, in my calculator, it's second, start. You do that first. And then you go over to the math menu. and you choose option 5, which looks like that guy. So you can either scroll down, but if you just hit 5, you get it. You then go back and you do second stat again. That gets you essentially list. Now you choose opts for options, I guess. And number 5. And this will get you a guy called sequence. And then you type in whatever this happens to be. In this case, n divided by the sign button. So let's put that in. N divided by the sign button. N, close the bracket. I guess I'll put it here because I don't have a lot of room. Comma. N, comma. 1, comma, 7, and finish with 2 brackets. And I should be able to hit enter, and boom. And of course I did something stupid. I think it's because I was doing too much. The instructions are correct because I got it a few seconds ago. And it was what? N divided by sine of n, comma n, comma 1, comma 7, couple of brackets. There we go. So those instructions are correct. I just maybe didn't do my own instructions. Are we cool with that guy now? So if there are some questions that ask you to do this or do that. And I think there's a question at the beginning where you don't actually do the sigma, you just fill in the 7 would go here and the x cubed would go there. So you don't actually do the calculator, you just type missing pieces to a sigma equation. Okay, are we good now? We're ready to move on to numerical. Right, get this out of the way. We are going to have to deal with estimating the area under a curve when the information that they give us is, to say the least, lacking in detail. So let's look at the first situation. Suppose you wanted to know the area under the curve and the information was given to you in the form of a table. Most likely question might be something like this, because this does happen. You know that you can have an experiment where at various times you measure the velocity of an object. So let's say at 0.5 seconds, at 1 second, at 1.5, and finally at the 2 second mark, right? And at these particular times in meters per second, the object was going 3 meters, 5, 6, 9, and then 13, right? Just for argument's sake. Now, you wouldn't need to do this for the question, but I'm going to do this because I'm a kind of visual person. There's time, there's velocity. Can you imagine that let's put the numbers in here, at 0, at 0.5, at 1.5, and it looks something like this. It's at 3, and then it got to 5, then it got to 6, then it got to 9, and then it got to 13. And can you imagine that all you really know are these key D points, but you pretend that there was a curve going through them, and what you're trying to do is find the area under the curve. But you're not given an equation. You're not told the curve is x cubed or t cubed in this case, right? You're not given every detailed point. You're only given little snapshots. But the snapshots are equally spaced, right? So I can look at this and I can figure out that delta t, which represents, if I put little lines in here, can you see my strips here? Can you see that that's going to be 4 strips? So even if they didn't tell me, I could tell it was 4. What would be the width of each rectangle? Because that's what delta t represents. On this table, what's the width?
0.5.
Exactly. Now, if they didn't tell me, although it's kind of obvious, you can look, but if they didn't tell me, wouldn't it just be 2 take away 0 divided by 4? Right, you'd still get it, 0.5. Now, let's suppose I decide to do L4. Right, that means that if I'm using this rectangle picture that I've just got here, won't L4 be these 4 rectangles? Right? Now, the formula, and I'm going to put more detail than you ever need to do. You'll skip half the lines I'm about to write down, but I'm putting it in just for completeness sake, so you can say, how did he get there from here, right? So you kind of see what's happening in the middle. If I was trying to find the area of these 4 guys, I'm going to introduce some nomenclature, fancy word for it. This guy here, this t value is called t0. This guy's called t1. This guy's called t2. This guy's called t3, and the last guy's called t4. That's how you name the points that make up the ordinal points that make up the split. So in this case here, it's delta t, the value of the function at t0, plus the value of the function at t1, plus the value of the function at t2, and finally the value of the function at t3. Now, if you look really carefully, I'll put it in green. Isn't t0 the height that I'm going to use for that first rectangle? Can you see it's this guy? For this second rectangle, isn't it t1? This is going to be t2, and this is going to be t3, and finally this is t4. Do you see that a left only uses these 4 heights? 0, 1, 2, and 3. In this particular guy, delta t is nothing 0.5. The heights of these rectangles are 3, 5, 6, and 9. So I'm going to just be careful here and add them all up using the calculator, although I should do it in my head. It's 0.5, according to what I have, 23, which is 1.5. So this area under the curve, using these 4 left endpoints, that generates these 4 rectangles. The area of that is 11.4. Now, what would that be in practice? Do you know that the area under a velocity time curve is the distance traveled? So the question might just say, use this table to estimate the distance traveled over that 2-second period, and using a left endpoint, the answer is 11.5 meters. Now, it wouldn't surprise me if they also asked you to find R4. Agreed? Now, that's going to be delta t. But if I used the right endpoints, won't I be using t1, 2, 3, and 4 to get the heights? So that's going to be the value of the function at t1, and then at t2, and then lastly at t3 and t4. So in this case, it's going to be those guys. Oh, darn it, in space. Oh, too late now. It should have been 0.5. 5, add 6, add 9, add 13. And I'll go to my calculator here, and I'll go 5, add 6, add 9, add 13. And I get 0.5 times 33, which is 116.5. Now, you notice I found these guys, when you do the left 4, do you see that you use the 4 numbers on the left? And when you do a right 4, do you notice that you're using the values on the right-hand side, right? The 4 on the right. So this bit here, and you know, you probably should be able to go to this bit here, right, without having to write down the earlier steps. That's, I guess, what I'm trying to say. Now, here's another thing. If the table's small, it's quite easy just to do these without, you know, looking at a connection. But imagine it was a table with 20 numbers in it, right, or 21 numbers more likely, right? If I wanted to do left 20, I'd have to do it the hard way. But see if I wanted to do the right 20, don't I just add this number and take away that one? So couldn't I use this total, add 13 and take away 3, right? Well, add 13 and take away 3, isn't that a net effect of adding 10? And if you add 10, do you see you get this answer? So that's a way in which you can reduce your workload. If you're doing a table and the table's quite big and there's lots of numbers in it, you have to find the left 4, the left 10, the left 20. You know, you have to just do it, right? You have to add them all up. You can't avoid that. But to do the right one, can't you just add the number at the end and take away the number at the beginning and change the total? Now, a last thing to do with this fella is, do you notice that in this particular case, the numbers are going up? Do you see it in the picture? They're going up. That's increasing. If your data is increasing or decreasing, you can say something even better. Isn't this an underestimate? It means, if you look at my picture, can you see that these rectangles are less than the real area? The real area is a little bit bigger. So that's an underestimate. On the other side, of course, wouldn't this be an overestimate? And I'm going to go back to my picture. If you use this fella here as your rectangles, can you see that the right-hand 4 are much bigger than the area? So if your function, if your data is always increasing or always decreasing, the biggest answer will be an overestimate and the smaller answer will be an underestimate, which means that you can say this, that the true area under the curve is somewhere between 16.5 and 11.5. So you've now got a bound. You know, okay, I might not know the answer very accurately, but at least I can tell you it's somewhere between here and here. That's a little bit better than saying, it's not a very good estimate. I know it's pretty bad, but it's kind of somewhere round about 16.5, or it's kind of somewhere round about 11.5. Do you see that's kind of vague and not very helpful? If you can do it, isn't this a bit more helpful? Even although the data is still bad, at least you've got a boundary and you say, well, I know it can't be 82. Another point, if this data goes up and then down, you cannot pick the biggest and say it's an overestimate and the smallest and say it's an underestimate, because if it goes up and goes down, some of the rectangles will be too much, but others will be too short, and you're not easy to judge which one wins, whether it's a little bit less in the, you know, overall or a little bit more overall. And you shouldn't really do guesstimating in this. You should only do it if it's allowed, right? It's guaranteed if it's increasing and decreasing that you can say this. Otherwise, don't make that assumption, because it is an assumption, it's not a guarantee. Are we good with how to estimate areas under curves using tables of values? So the second situation where you're going to have to deal with data numerically rather than the sigma notation, is when the information is given as a picture, a graph. So I apologize by how bad my graph is going to be, but I'll do my best. So let's have a scale here that's 5, 10, 15, 20, 25, and 30. And let's have this at 2, 4, 6, 8, 10. I'll do. And right, so we have some function, but we don't know, they're not going to tell us the formula for it. So it's not y equals x cubed or sine x or anything, it's just a label. This curve, this weird kinky curve, is called y equals f of x. Excuse me. And we're going to start at 2, and we're going to finish at 10. And we're being asked to find the area under the curve. And we're going to do it with 4 strips. So far, so good. So that's the setup. How do we generate an L4 and an R4? And then we'll work from there. Excuse me. Well, you don't need to create a table, but I'm going to. You can choose to or not. We're going to start at 2. Since it's 4, won't delta x be b take away a over n? And if you start at 10 and you take away 2 and you divide it by 4, you get 8 divided by 4, you get 2. So it's not a surprise that those are going to be the numbers in my table, right? 2, 4, 6, 8, and 10. Now the tricky part. I'm going to have to figure out what these numbers are myself. I'm going to have to go here and do a guesstimate of what values it is. And I'll try and be as accurate as I can, but it's not going to be easy. I'm pretty sure that that's 5. At x equals 4, it's maybe 8 or 9. I'm going to call it 9. At x equals 6, it's about 16. At x equals 8, I'm pretty sure it's 25. And at x equals 10, I'm pretty sure it's 30. Are you comfortable where I got these guesstimates of the values? Now, you're going to be some variation in that. You know, Arwen, you're going to do it and you're going to see a 17, and you know, Javon, you're going to do it and you're going to see an 18, right? I can't tell you who's right. I might think it's one of you, or I might not. I might think it's the other one. I may even think it's a totally different number, very close to those. It does mean that when you're checking your answer, the homework, the software is very unforgiving. So you could be doing it perfectly correctly, but because you thought it was a 17 and the book thought it was an 18 kind of thing, that your answer is a little bit different from theirs. If you end up having 3 shots, because that's how many shots you're allowed, and at the end it says you're wrong and you had 18 as your answer and they said it was 17.5, if you shoot me an email, I'll give you the point, because you really did it right. I don't think it's fair to ding you on. I mean, you might be disagreeing with some of my answers here right now. You might think, I don't know why he thought that was 16. That looks more like 17 to me, right, or whatever. So we got this data. Now, once we get this data, can't we basically just do this guy? Right? So I'm going to be doing, oh, that was bad choice, or good choice, I guess. Let's do L4. Delta X is 2. And if you're doing left 4, don't you just use those 4 guys? The 4 on the left. So that means I can just say 5 add 9 add 16 add 25. And I'm going to cut some corners here. And 14, 30, 55. So it's 2 times 55. And I make that 110. We're cool with that? The area under this curve is 110 units. Let's do R4. Well, won't it be delta X? Now, if you're doing R4, don't you just miss the first term? And so the numbers will be 9, add 16, add 25, add 30. And that's 55, and that's 25. So 55 and 25 is 80. So 2 times 80, I believe, is 160. Can I say that this is an overestimate and that this is an underestimate? Look at the picture. Is it going uphill? It's never going downhill, right? So if it's going uphill, overestimate, underestimate. That means that we can now say that the area is somewhere between 160 and 110. And the overestimate is 160 and the underestimate is 110. I like seeing faces because it gives me an idea if things are working. I think things are going good, but I can only see about 8 of your faces. Is there anything that I've done in the last couple of questions that you might want me to talk about a little bit more? Or do we feel good right now? So if you get a table, you do it numerically, right? If you get a graph, I would suggest you make a table of it and then you can do it, right? Because basically then, don't they all become table questions? You either get the numbers given to you or you go to the graph and you write down the numbers instead, but it's still basically a table in both cases. Right. So what I'm going to do now then, if that is working fine for you, is I'm going to go and we're going to look at some of the homework questions. If I can leave for a few moments. Oh. Darn it, this is a pain in the butt. Where are you hiding? Ah, here you go. Gotcha. I'm just waiting for it to load up before I come back out and in again. And there we go. And it looks like it's good to go. Right. One of the unfortunate things about this particular set of homework is that the questions are quite jumbled up. It would be nicer if all the sigma were in one place and all the tables and graphs were in a second place and the sigma stuff came at the end. So when you're doing your homework, there's some questions I suggest strongly that you just miss until we've actually covered the work. So give you an example. Right now, question 1 is basically just fill in some missing guys. So let me do this one. You're going to do 1 squared, 2 squared, 3 squared, 10 squared. So it's going to go k equals 1. Would you agree that in this story that's 10? Now, what would go in here to make this sum happen? What function of k would you use here to make that happen?
K squared.
K squared. Now, I don't think I can actually, because of what I've got, do the real K squared. Oh, there we go. I can. And I don't have it, but you know you have a little submit button and boom. If it's right, you move on. If it's wrong, you know, kind of mistakes people make. You know that because I've been doing the calculator, almost every sigma is n equals, but they could be k equals or p equals or something else. So sometimes you forget that and you say n squared. Well, it's not n squared because isn't this counting variable a k, so it has to be k squared. Right. So that's just a little thing. Would you agree k equals 2, question 2 here, isn't that basically sigma calculator? Won't the only difference be n equals 0 and 10? So it won't be a k, you'll be doing an n. Skip 3, because we haven't covered it yet. Here we go. Question 6 is a table question. Can you see the numbers? Looking at that number, tell me who delta t is. Looking at that table, I should say. What is delta t?
0.5.
0.5.
Agreed. If you were going to do L5, then won't you use all the numbers except these guys? These, well, I can't do it. See these guys, I'm trying to get my mouse pointer to cover it. Won't you just use the numbers from 0 to 19.8? Right? Won't that give you L5? And if you cover up that guy, cover up that first one, won't those guys give you R5? Now, have you noticed that they don't say at the top, find L5, find R5? They just say find smallest and largest. Isn't this table increasing values? So won't the big answer be the R5 in this case, but one of your two answers, the big one, and won't the small answer be the small value? So it's not that they are not doing the table stuff, they're just not handing you on a plate, right? Oh, by the way, there's 5 strips and that delta t is 0.5 and I want you to find L5 and R5, right? They didn't phrase it anything like that. Didn't they just say, here's a table, find the upper and lower estimates for the distance? Because the area under that curve is the distance. That's why that works. Right, here you get a different fella. What is, right, it says when we estimate the distance T0, they are not equally spaced. It says we can still estimate the distance by just basically taking this data. And so this is a one-off question. If you wanted to do an estimate of this, if you go 0 to 10, would you agree the bottom would be 10? And wouldn't the height be 180? Or 0? I'm picking the right-hand side, 180. And then 10 to 15, wouldn't the gap here be 5 and do 319? And 15 to 20, the gap would be 5 and 442. And if you go through that, you would be able to get an answer. And since they want the upper approximation, the one I just told you is correct. I don't think I explained that well. Do you want to see what that would look like? Or did I explain it well enough that you know what I was trying to get across?
Love to see that.
I would be in the same boat if I was listening to me. So I'm not going to pick that one because you only get one shot of it, but I'm going to pick a table that's got the same features, right? So if you give me a few seconds, we'll kick out of this and I'll create the table and we'll look at this one-off situation of how you deal with not having equally spaced data points, right? So let's suppose, oh, I don't know, I'll call it t, and who cares, function of t. And it goes 0, 2, 5, 10, 12, 14, right? So you notice that they're not evenly spaced, so there isn't a single delta t. And let's suppose in this particular table the numbers are getting bigger as you go along. So it starts off with 3, and then it goes 7, 8, 12, 15, and finally 20, right? So that's my version of the same kind of table that they had, right? Different space values, but increasing. Now, you don't need this, but I'm going to try and draw it because it's kind of visual what I'm about to do, and I think it helps, at least it helps me. So there's 0, there's 2, there's 5, there's 10, there's 12, and finally there's 14. And then at 0, the answer is 3. What do I need? 2, 6, 10. So 4, 8, 12, 16, 20. I'm just picking a scale to get it to fit. Right, at 0, it's 3. It's about there. At 2, it's 7. It's about here. At 5, it's 8. It's actually on the dot. At 10, it's 12, which puts it about here. At 12, it's 15. It puts it about here. And at 14, it's 20. It puts it right here. So can you imagine we've got a kind of curve that looks something like that? Right. Now I'm going to put in the numbers 0, 2, 5, 10, 12, and finally at 14. Even in my badly drawn picture, can you see that the rectangles that I'm going to generate in a few moments from now are different widths? Right? Some are wide, some are not. Since I want the answer that's going to be the big estimate, if I take my first choice here, do you see that it would be a good idea to pick that guy? And then for my second fella, I'm going to pick that guy. And my third fella, I'm going to pick that guy. And then this fella, and finally this fella. So when I find these 5 rectangles and add them together, won't that be my overestimate for the area? And that's what they want, right? The overestimate in this case. I'm not going to write down any fx0s and fx1s. I'm just going to do it pretty crudely. See this rectangle here? I'll call it rectangle 1, rectangle 2, rectangle 3, rectangle 4, and say rectangle 5. I'm just giving them labels. I'm going to find the area of each one of them totally individually. And then don't you just add them all up and that's the answer. Right, rectangle 1. Would you agree that it's 2 units wide and 7 high? Are you happy where the 2 and the 7 are coming from? 2 times 7. Right, the second rectangle. How wide is that rectangle?
3.
3. How high is that rectangle? Is it 7 or 8 high? How high is this rectangle?
8.
8. Right, it's on the bigger side. So 3 times 8. The third rectangle, can you see that the third rectangle is 5 wide, right? And is the third rectangle, is it 8 or is it 12? How high is this rectangle? 8?
Oh.
Right. Have you noticed that when I have a choice, I always pick the bigger one? Right. Now, if I go to the next one, it's only going to be, what, 2 wide? And won't it be 15 tall? And the last one's going to be also 2 wide, but won't it be 20 tall? Are you comfortable about where these widths and heights have came from? That's what I was trying to describe earlier, but there was just too much, I think, verbally. Now, if you take this guy is 14, you take this guy, that bit's 24. This rectangle will get you 60. This one will get you 30, and this last one will get you 40. So 8, 4, 7, 13, 14, 15, 16. Our answer would be that the area under this curve as an overestimate would be 168. So I know that it's 168 or probably less. if I wanted to do, I'm not going to do it because we don't have time, but if I wanted to do an underestimate, because you could do that, wouldn't it be the same basic starting point, but wouldn't I be using the smaller of the two heights? So can you imagine it would be these rectangles here. And can you see those guys would generate, instead of 7, wouldn't you use 3 here and 7 here and so on? And that would get me an underestimate. So I could actually do 2 versions if they asked. That makes sense? No. Okay. So let's stop sharing that for a moment. Actually, I've only got 5 minutes by watch. So for the time I've got left, I'm going to go and do something a little bit different. We already have, well, you don't want to see that. We already have some stuff added to your course. So, are you looking at a Canvas page right now, or shall I have to do that out and in thing again?
No, we're still seeing you.
Okay, now the 2 places that have added information. The first place is going to be under Zoom schedule and video. So when you click on that and you scroll down to week 1, do you see that yesterday's video is now there? Can you actually see that, or will I go out and in again?
You haven't shared your screen.
I haven't shared that. Okay, so I'll need to go out and in. It's weird that sometimes it will do it and sometimes you have to go out and in to share a screen. Right. This is if you go to the Zoom lessons and what's its title? Zoom schedule and video lectures. If you go to that, you'll now see that yesterday's Zoom. So if you miss a day, this is where you go to find the lesson, like today's lesson, and you can watch what's going on. It is edited, so I cut out the stuff at the beginning where I say hi to everybody, because I don't think you want to watch a video saying hi to everybody. And I tend to cancel out stuff at the end, because sometimes people hang about at the end to ask me something, and I don't think they need that to be shared. So if you wonder why the video might look shorter than you recollect the lesson being, it's because I took things out that I don't think you needed to see. What else? Oh, and there is a second place. This probably won't work, but here goes. If you just go back into the homepage and you go to Chapter 5 Video and Lectures, and you go to Section 5.1, you probably can't see that, can you, guys? Oh, you can actually, it's a go figure. Do you notice at the bottom, I've actually got a short video that actually takes you through the button presses that you need to do the Sigma. So if you want to actually see a video and you can pause it and say, okay, what button is he pressing again? I'm using the emulator there, so the calculator's much bigger, so it's probably a little bit easier for you to see what I'm doing as well. And so as the weeks go by, other things will be added. What you might not have noticed is that if you go to this particular site, I already have stuff to help you. For instance, if you go here, here is how to use your calculator to do Sigma. And now it won't be as small as that. If you hit this, you can get a bigger version eventually. Boom, 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 boom. There, right? So you can actually see it there. And there are lots of other things here as well. Here is me just going through some of the stuff that we did today in a much more general way. So what happens if you split something not into 5 strips or 4 strips, but N where n could be any number, right? So this generalizes it, but it shows you how to do left and right. And here is an example of a table being used. Here is a graph being used. Here's a table version. So if you look at this one, all I've done is write it down using Sigma notation, but it's essentially, we did it kind of at that line onwards, right? But I put more stuff. I always think it's a good idea to tell you more than you need rather than less than you need. So you might look at this and say, well, I don't really need to know that. I just need to know how to get that bit to get the answer. But it's there. So there's worked examples, all the kind of cool stuff that you need. So, you know, use it. I mean, it's for your benefit. It's hopefully, anyway, it's for your benefit.